In the previous video, we developed a function which would allow a set of mathematical optimization functions to be evaluated. These functions included the Beal, Ackley, Cross-and-Trait, and Levi functions. If you haven't yet seen this video, I highly recommend checking it out as the code produced will be used in today's video. And just a quick update before we dive into the video, I did actually go back and add a few more optimization functions. I added the bulking function, so the bulking function, the wave drop function, the Goldstein price function, the egg crate function, the Booth function, the Matches, the Himmelbau, the Holder table, the McCormick, and with the aims that these will give us a broader overview of all of the optimizations we can perform and how they perform on different search spaces. I've also adjusted the ranges function accordingly to just incorporate the new optimizers, but you can go through and do this in your own time as well. There is no problem there. You can see the code here. But today we're going to be jumping into the BAT algorithm. So it's going to be our first optimization algorithm, and it is a meta-heuristic algorithm. I'm going to be following this paper that was written by Yingji Yang, who actually, I believe, theorized this concept and brought it to light. So it mimics the echolocation of bats, it applies a set of dynamics to the bats, and then they move through the search space. So let's jump straight into it with our BAT algorithm. Now, we're going to start by just making sure every time we run it, we clear the workspace, and we're going to first just add a path to the previous code. So this is going to be different for everybody. This is my relative path, and I think it's this. So I need to work out where it actually is first. Next, I'm going to start defining the BAT algorithm settings. So these will just be what runs every single time we run the script, such as the population size. We're going to have a maximum number of movements. So these will be the movements that will be performed by the bats, and when this number of movement expires, the algorithm will stop. So the dimensions of the problem for us, it's a two-dimensional problem because we have only an x and a y coordinate. We'll set a frequency minimum to be 0 and a frequency maximum to be 1. If you're unfamiliar with any of this terminology that I'm using, as I said, it is all in this paper. Sort of all of the echolocation parameters and the dynamics of the bat. So we're going to have a loudness of 0.5, and this is the rate at which the bats will reduce the loudness of the echolocation. We will set our pulse rate to be 0.5, and this will be initialized by a random walk. And then we're going to have a gamma decay value of 0.5 for the pulse rate, and we're going to set the accuracy to be 3 decimal places. So we will now select the optimizer function we wish to optimize. So for the first one, we will select let's do the Ackley function. So we're going to select the Ackley function, and then in the same way we did previously, I'm just going to quickly run this to make sure. It won't let me run that. I just want to make sure we have the auto completions for this path. So x range, y range is equal to the optimizer ranges of the optimizer. Now we're going to initialize our bat population. Now we could do this one of two ways. We could just generate the array based on random values, or we can do it inside a for loop. And the reason why I prefer to do it inside a for loop is so we can actually analyze the fitness as we go along. So every bat that's generated, we will analyze its fitness. So the population, so for the population I1 is going to be a function of the x range 2 minus the x range 1. Now I wish MATLAB had a better way of generating values between other values from a normal distribution, but they don't. So this is how we have to do it. If I could spell. And then we will analyze the fitness of our bat. And it's going to be the population of I1, the population I2, the optimizer, and then the mode of operation is optimizer. So when we run this, if I just run the entire script, not sure what's wrong here. Good Lord, it's because it wasn't a value. Population. Right, there we go. So now when we look at our population, we have generated 50 bats that all have an x and a y value that is between the x and the y range, which for the Ackley function is -5 to 5. And we have generated a corresponding fitness value for all of the bats. So we now want to just rank the bats. So let me just get some space here. And we'll say the best, well, we'll not rank them, but just basically grab the best bat is the minimum of the fitness. And then we're going to start initializing the bat dynamics. So we've got a bat loudness, and we're going to set this to be all equal to 1s. It's going to be of the population size with 1 column. The bat pulse rate is going to be the same but with 0s. The bat frequency is going to be again 0s of the population size, but there's a frequency for each dimension we have. So we will set the dimension, and then we will set the bat velocity to just be equal to the bat frequency, because it's the exact same thing right now. And this was going to be a plot the bat locations. Now this is going to be our first function, so we're going to edit population points, and in this population points we're going to have a points returned based on our current location of the population within the search space. So this was the reason why in the previous video we coded up the contour map, as we're going to use that contour map to display our population. So we're going to check to see if the points are empty. So if is empty points, it means we haven't yet initialized our population plotter, and we're going to create our new figure. We're going to clear the axes, and we're going to hold on, and we're going to say optimizer, optimization function, and we don't need a query point. It's going to be of the optimize that we passed into the function, and it's going to be a contour map. We're then going to look and say if we have got a points variable. We did this before. We just want to reset the points, and then we want to reinitialize the points as a scatter of all the population values. Now this is not the most efficient way of doing this, computationally speaking, but it is a solution, and it will solve the problem, and you'll see it's quite a fast solution. It could be faster. And we're going to add a small pause of 0.1 seconds just so we can see the bats when they are being populated throughout the iterations of the simulation. So now we're going to say that points is equal to population points of the population we just created, the optimizer, and we've got no points right now. So when we run that, what we get is our search space that looks like this. As we said, it was the Ackley function. This is the contour map of the Ackley function, and all these black points represent the current location of a bat. Right, we can now start to actually run the entire simulation. So run the simulation. We're going to perform a tick so we can just timestamp. And we're going to say for movements is equal to 1 to the number of movements. And then we're going to say for bat is equal to 1 to the size of population. So what this means is we're going to iterate through each bat. For every movement, we will iterate through the population of each bat, and we're going to update the dynamics. We're going to perform a random walk, and then we're going to update the fitness. So let's start with the dynamics. We're going to calculate the bat frequency. So the bat frequency of the bat is determined by the frequency minimum plus the frequency maximum minus the frequency minimum times by a random vector of 1 to the dimension size. Then we're going to determine the bat velocity as being a difference between the current best bat, which was the reason why we had to calculate this index value here, and the bat we are evaluating. So we're going to say the best bat minus the current bat, and then that is times by the bat frequency as a piecewise evaluation. And then rather than updating the bat population, we actually create a new variable called position, which takes in the population position of our bat and then adds the velocity to it. So this is how much we will move in one iteration, and this is due to the fact that we don't update the bat population unless the fitness gets better. So we do not want our bat to update unless it's a certain value. Right, so to diversify the population, we apply a random walk. So we will say if a random value is less than the pulse rate, so this is where the echolocation comes in now. If it's less than the pulse rate of the bat we are currently trying to move through the search space, then we take the position we just calculated, and to that position we add a small deviation. Now this deviation can be a fixed value. You could do it as like 0.01 or 0, whatever you want to do, but we are actually going to use the loudness of all of the bats, so the mean bat loudness times by a random vector of dimension. Now that just occurred to me, I called it dimension, I've called it dimensions here. And this will just add a small random walk, and due to the way the echolocation works, as we move through the search space, we will begin to reduce our loudness, meaning that our random walk will become smaller to allow us to home in on the global solution. So before we identify the fitness, because we are doing a random walk, we need to make sure we have not exceeded the search space. So we are going to scale the population, And this is going to be our second function. So edit population scaling. And all this is going to do is just ensure that we are not moving outside of the search space. So we have population scaling of the population and then X and Y. So what we're going to say is, we're going to say that the population that we are putting in, if we can evaluate the index of the first, so all of the first rows, sorry, every row in the first column, if that is less than the x1 value, then we will say set that value to the x1. We will now evaluate the exact same column again, so all of the rows in the first column, but if they are greater than x2, then we're going to set it to be x2. And we're going to do the exact same thing for the second column. So if all in the first row are less than y1 in the first column, we're going to make that be y1. And this is how we are just going to ensure that we do not exceed, they should be 1s and 2s, we do not exceed our search space. So let's jump back to our BAT algorithm, and we're going to say population is equal to population scaling. We're going to apply our population, our X range, and our Y range. Next, we're going to update the fitness now. So we've ensured we can't go outside the search space. So now we're going to add our query to the optimizer function. So fitness value and the target is going to be equal to optimization function. And we are putting in, that's a good point here. This should actually be position, not population, because we are not updating the population yet. So what we are passing into the optimizer function is the position, and it's the position 1, position 2, the optimizer, and we are running it in mode optimizer. So, and now what we need to do is check the fitness. I'm not going to write a subheading for this. We're just going to say that if our fitness value is less than the fitness of the BAT from the previous iteration, did I call that the correct thing? I did. Then we're going to say that the fitness of the BAT is now equal to the fitness value. We take the population and we make it the position, so we update the position of that BAT. And then we need to decay the loudness. So that is performed by using that loudness function from the start, and then we decay the loudness of that BAT. And then we need to increase the pulse rate, and for that we're going to use an exponential relationship. So we're going to take the pulse rate times by 1 minus the exponent of the gamma variable that we calculated, initialized at the start to be 0.05. And we multiply that by the amount of movements we have currently done, meaning that the exponential will grow and then it will grow very fast at the start and very slow towards the end. Now we're going to check to see if this fitness value is actually better than the best. If it is, then we change the index to be the best, and we change the best to be the current fitness value. And that is the BAT algorithm. That should be the BAT algorithm coded. And one final check, and we should be able to round off this. So at the end of each run, we're going to update the points so we can see where we are. So population optimizer, we've already done the points now, so now I'll just go to a new one. And we're now going to end the simulation. We're going to grab the time taken to compute. I'm going to let ourselves know simulation ended after seconds with this many movements. A new line, and then we add our t and we add our movements. And we can now just say that the best solution is x is equal to 5 decimal places, y is equal to the same to 5 decimal places. I'm going to say with a fitness of 5 decimal places, and then a new line again. And then we're going to type in the population of the index 1 and the population of the index 2, and then in fact we need to type in at best. And that should be our BAT algorithm. So let's run that, see if we've got any errors. We do. So index in position 1 is invalid. So BAT velocity, they're all 0. One of them appears to have suddenly died there. What does the BAT frequency? Yep. Index in position 1 is invalid. Aha, okay. So if I just run that, the best index 30. So why did the index update? My apologies, that should be BAT. So there, rather than I set that to be the best, so it just decided to overwrite it with the fitness, it should be the BAT, so it will update the index with the BAT. So if we run that again, there we go. You see all the BATs converging onto that global solution, and the problem we've got now is the simulation is still running despite us getting to the global solution. And I appear to have made a doozy there as well. There we go, so let's fix that. And the simulation took 8.5 seconds. If we were to come back to our population points and just remove this pause statement and then rerun, see it's much faster. But again, we were still running the simulation despite having converged onto the solution. And this is where our accuracy comes into it. So we're going to, at the end of the simulation, so just before we run this, we're going to say if we round the best value to the accuracy, so we're rounding the best value to 3 decimal places, if that is equal to the target rounded to the same accuracy, then we're going to break the simulation. It's going to end, and there you go. It ended after 11 movements. We converged onto the solution to 3 decimal places, and it's been successful. So now we can try a different function. So let's try the cross trait. We got there after only 4 movements, and that's the beauty of the cross traits. Because there's 4 global solutions, we've got 4 times the chance of converging, and that was pretty much about what we converged by, 4 movements as opposed to 11 to 12 movements. So what we'll say is we'll just put end condition, and if that is false, we'll say if the round, we'll say if this round is equal to the rounded target and the end condition. So there we go. We ran for the full 50, converged, and we did converge onto the solution. We can say true. There we go. We could add something else, and we could say something like and movements is greater than 10, just to make sure we have to move 10. So we did 11 movements, 11 movements, 11 movements, and so on. But we will just remove that statement for now, but that is something you could play around with. And I think that's probably about it for the BAT algorithm. Let's run it through a few more, because one of the things the BAT algorithm I've noticed struggles with is the Beal function. It did get there, but as you can see, it didn't actually end the solution. It did end the solution there, it converged there, and it converged there. And one of the problems I think I always have with this is the Beal function being a very shallow gradient means that sometimes the bats can not move through the space. Of course they are doing now, but as you see there, these ones actually found a secondary solution. We did actually find the other solution, not to the level of accuracy we required, but as you can see, some of the bats actually converged onto a secondary solution. So which other functions do we have? Let's look at the holder table. We did get there. I'm not sure I agree. There maybe this needs to be 2 and this needs to be 1 because we inverted them before, didn't we? So let's see if that fixes that. Yes, there we go. So the contour was actually the wrong way around because of the way we'd, in the previous episode, inverted the axes. And again, we've found the solution, 13 steps. Again, let's look at some of the other functions. So let's look at the egg crate. Seven movements, 6 movements. So very fast again. You can see the bats converging. Let's put that pause back in. See the bats all flying towards the solution. Now, one of the functions I haven't tested before is actually the Himmelblau and the Booth function. So we'll test these ones together for the first time. So the Booth function, we reach the fitness, and again, let's try the Himmelblau, if I can spell that correctly. We actually got there very, ooh. So there is 4 solutions to the Himmelblau, and you can see these ones seem to be stuck in some sort of no return gradient where they are probably moving, but they are not changing fitness. And these ones are, so that is probably why these are completely stuck. Yes, so you can see how having multiple global solutions affects where you converge, and it's quite random as to where you will converge on the solution. What other ones should we look at? Let's look at the Goldstein price and the Levi. So Goldstein price. So we have converged, and then let's look at the Levi. And yes, the Levi, straight away we reach the global solution. So that's going to wrap it up for this introduction to the BAT algorithm. If you enjoyed the episode, please do leave a like and subscribe. If you've got any questions, leave them down below in the comments, and I'll see you in the next video.